Hi class, this video presents a brief tutorial on atmospheric stability. Now this tends to be one of the more difficult concepts that we cover in this class, so hopefully this video can help clarify some things. Specifically what atmospheric stability actually is, its purpose in terms of cloud formation, and how we can use basic lifting concepts to determine atmospheric stability and where clouds may potentially form. Recall that clouds form when the air becomes saturated, or in other words, when the temperature and the dew point become the same value. Creating a cloud requires three ingredients: moisture, which can ultimately become the cloud itself when it saturates, an unstable environment, which will favor rising motion, and some kind of trigger that will ultimately provide the initial lifting that forces the air up. This video, of course, will just focus on the stability piece. Stability ultimately refers to a condition of equilibrium, where an object is either stable or unstable. Now there is a third condition known as neutrally stable, but for this class we're just going to focus on stable versus unstable. So let's just try to visualize what I mean. You notice the two scenarios pictured: boulder A lying in a valley and boulder B lying at the top of the hill. Let's say for whatever reason you decide to start pushing boulder A up the hill. Well, what happens if you let go? Obviously it's going to roll back down to the bottom. In this case the rock is stable, because once you move the rock and let go, it ultimately returns to its initial position. Now in the case of boulder B, it only takes a slight push to get it accelerating down the hill. In this case, the boulder is unstable, because after the initial push, the rock accelerates away from its initial position. This is actually analogous to atmospheric stability, except we need to picture our hill configuration upside down, and instead of a boulder, we need to think about a mass of air, which we will refer to as an air parcel. Now this air parcel is going to be considered unstable when its initial push upward and then letting go results in the air accelerating upward on its own. This is ultimately how thunderstorms are created: deep convection produced by unstable air that's rising, producing an updraft. It's essentially a buoyancy process, where lighter, lower density air wants to sit on top of heavier air of higher density. This is where the phrase warm air rises comes from, because if a bubble of air is warmer than its surroundings at the same pressure or altitude, that air is relatively light and it's unstable, so it will rise on its own. The air can cool and saturate as it rises, forming a cloud. As long as the air remains unstable, the cloud will continue to build, and the updraft will get stronger. Once the rising cloudy air of the thunderstorm encounters a tropopause, it will usually become the same temperature or colder than the surrounding environmental air. Here, the storm becomes stable and spreads out laterally, since it can no longer continue to rise. This produces the anvil feature commonly seen in thunderstorms. Remember that temperature increases in the stratosphere, but an air parcel in a thunderstorm is going to cool as it rises. This is why the tops of thunderstorms rarely extend into the stratosphere. In other words, the tropopause generally serves as a lid for thunderstorm growth, because the stratosphere is extremely stable and doesn't allow for any more free convection. Here's an example time-lapse of a developing thunderstorm. You can see the instability at work here as the cloud builds vertically. The cloud growth looks chaotic and intense, but at a fundamental level, it's simply warm, moist air being forced to rise, saturating, and becoming unstable, which allows the storm to continue to rise and ultimately reach the top of the troposphere. In order to think about cloud formation and potential thunderstorm development, we need to become familiar with the concept of the air parcel. This is essentially the air that might be lifted from the surface, saturate, and form our cloud. Parcel theory is not perfect, but it allows us to work with observations taken by a radiosonde and get a pretty good idea regarding the local atmospheric stability and potential for thunderstorms later in the day. Now imagine this parcel of air as an air bubble wrapped in invisible elastic wrap, initially located at the ground. The air parcel cannot mix or exchange energy with the outside environment. However, its volume, temperature, dew point, and pressure can change as the air parcel rises or sinks in the troposphere. Now we must remember that barometric pressure decreases exponentially with height, so if the air parcel were somehow forced upward, it encounters lower pressure. Because of this, the air parcel equalizes to the same pressure by pushing out against the environment. Thus, its volume will actually increase. But now that the air molecules inside the parcel have a larger volume to move around in, they make fewer collisions with each other, and they start to slow down. And if you remember that air temperature is related to the molecular motion, it should make sense that the temperature inside the air parcel will now have to decrease. Thus, the air parcel will cool and expand as it rises. This is a key concept that ties to cloud formation. We can quantify the rate at which an air parcel will cool as it rises. And if the air remains unsaturated, where the temperature inside the air parcel is greater than the dew point, this is called the dry lapse rate, and it's 10 degrees Celsius per kilometer. So for every 1 kilometer that an unsaturated air parcel is lifted, it will cool by 10 degrees Celsius. On the contrary, an air parcel will warm by 10 degrees Celsius for each kilometer that it sinks, because the air is compressed under higher atmospheric pressure. Determining cloud formation relies on careful monitoring of the air parcel's temperature and dew point as it rises. Remember, if the temperature maintains a greater value than the dew point, the air is still unsaturated and there is no cloud. Once the temperature and dew point become the same value, the air is now saturated and a cloud will form. We mentioned that dry air will cool by 10 degrees Celsius for every 1 kilometer that it rises. Well, it turns out that the dew point of unsaturated air will drop off by 2 degrees Celsius every kilometer. The amount of water vapor in the parcel doesn't actually change, but the dew point is dependent on pressure, which is decreasing as we climb to higher altitude. So as an initially dry air parcel is lifted, it expands and cools, and since the temperature cools at a much faster rate than the dew point, at some altitude, the temperature and dew point will reach the same value. This means that as an air parcel rises, its relative humidity increases because the air is getting closer and closer to saturation. If the now cloudy air is continued to be forced upward, or if it's unstable, the cloud continues to build vertically, while the temperature and dew point have to remain equal to each other. However, the air will continue to cool as it rises, so the dew point must go down as well. This means that more water vapor is being condensed to keep building the cloud. Remember that condensation is a warming process for the air parcel because energy is taken from the water vapor as it turns to water to warm the air parcel. This is called latent heat. And because of this heating, cloudy air will cool at a slower rate as it rises compared to unsaturated air. This is known as the moist or wet lapse rate, which is about 6 degrees Celsius per kilometer in the lower troposphere. This added heat can also help keep the cloudy air unstable, which can aid in the cloud growing into a thunderstorm. So if we're given some basic observations at the surface and in the lower troposphere, how do we use these concepts to determine where cloud bays might form and whether a cloud is expected to form at all? For now, let's tackle the first question. In this example, the surface temperature is 30 degrees Celsius and the dew point is 6 degrees Celsius. Now this air initially at the surface is not saturated, so we have to lift it to achieve saturation. Now, for dry lifting, the temperature will drop 10 degrees Celsius per kilometer, the dew point will drop by 2, and we have to keep doing this every kilometer until the temperature and dew point become the same value. And you notice that that happens at 3 kilometers. So it's this level where we would achieve cloud base if we took the air initially at the surface and lifted it to saturation. Now it's a little more complicated to determine whether or not a cloud will actually form and how tall it will grow, because we'll now have to additionally consider the stability of the environment. An air parcel will only be considered unstable and rise on its own if it's warmer than its surroundings. So we'll need to know the profile of atmospheric temperature in the environment, which we'll get from a radiosonde. Let's take a look at some different environmental temperature profiles, each characterized by a different lapse rate. Let's take a look at this first example. We take our radiosonde and we measure the profile of temperature throughout the lowest 4 kilometers of the troposphere. And we have 30 degrees, 26, 22, 18. So our lapse rate is 4 degrees Celsius per kilometer. That's the rate that the temperature in the atmosphere drops off. So we define our air parcel as the surface temperature, 30 degrees Celsius. Well, remember, this air is, if we assume that it's dry, is going to cool by 10 degrees for every kilometer it rises. And you notice it's colder than the air around it. By the time we get to 2 kilometers, it's 10 degrees, and the air around it is 22. It becomes 0 at 3 kilometers, and the surrounding air is 18. So if we let go of that air parcel, it is stable, and it's going to want to sink back down to its original position, where it becomes the same temperature as the surrounding air. We won't be able to make a thunderstorm in this environment. If we take a look at the second scenario, again, we build our radiosonde. Now you notice that we have a lapse rate of 11 degrees Celsius per kilometer. Notice that for every kilometer we rise in the atmosphere, the temperature drops by 11 degrees Celsius. That's what I mean by the environmental lapse rate. So again, we take our air parcel to be the surface temperature, and we go ahead and say that it's unsaturated. So it's going to cool by 10 degrees Celsius per kilometer. We push the air parcel up, it cools down to 20, and now you notice the air is warmer in the air parcel than the air around it. It gets up to 2 kilometers. Where 10 degrees, the surrounding air is only 8. At 3 kilometers, it's 0 degrees in the air parcel. It's colder out of the air parcel. So if we let go, the air parcel is less dense, it's warmer, and it's going to actually rise. This is an unstable environment because the air is able to rise on its own. We can make thunderstorms from this. Now oftentimes we'll have what's known as a conditionally unstable environment, and that's where the air parcel is initially stable, but if we lift it high enough, it actually becomes unstable, and then if we let go of the air parcel at that point, it continues to grow upward to a thunderstorm. Notice in this case that we're labeling the temperature every half kilometer, or 500 meters, and that the temperature goes down by 4 degrees Celsius every 500 meters. So let's take a look at what happens to this air parcel. It starts at 30 degrees Celsius, but let's say that its dew point is 22 degrees Celsius. So now we're taking into account how the air parcel wants to rise or sink compared to its surroundings, but also is the air saturated or not. And you notice that we are not saturated yet, but let's see what happens as we lift the air parcel. We'll cool by 10 degrees Celsius per kilometer. The dew point will drop by 2 per kilometer. And because of that, we'll actually saturate at 1 kilometer above the ground, where the temperature and dew point are both 20 degrees Celsius. Notice that the air is still stable because the air parcel is only 20 degrees Celsius while the air around the air parcel is warmer at 22 degrees Celsius. If we let go of this air parcel right now, it's going to sink back down to the surface. But let's say that we have some ability to continue to lift the air parcel, and let's see what eventually happens. Because in this case, the temperature and the dew point are the same, but the air is now only cooling by 6 degrees Celsius per kilometer. Remember, now that we're making a cloud, there's latent heat being released due to the condensation, and this air is cooling off more slowly as it rises. So we're still stable, and then as we lift the air another 500 meters, now you notice that the air parcel of this developing thunderstorm is now warmer than the surrounding air. So now, at any point from here, if we let go of the air parcel, it's going to be able to lift on its own, and the cloud is going to continue to build until the temperature becomes the same as that around it, and this occurs at 3 kilometers. So now if we lift the air any further, the air continues to cool, it'll be too cold, and it'll sink back down to its initial position. So in this example, we started out with an air parcel that was unsaturated and stable, but by lifting it to saturation and a little further, the air actually becomes unstable and grows a cloud that's about 2 kilometers thick. The main point here is that it takes an unstable atmosphere to allow clouds to form by saturation and to grow vertically into thunderstorms, or what we call cumulonimbus clouds. The greater amount of instability in the atmosphere usually means that the thunderstorms can grow taller. Now, of course, there's varying degrees of instability. Sometimes we have a weakly unstable layer where air grows, saturates, and forms our cloud, but the air is only unstable through a thin layer and then eventually becomes stable. And then there might be days where the atmosphere is extremely stable and you can't form clouds due to instability. On days like this where you do get a cloud, it's actually because you have a warm front or cold front that's forcing the air up to saturate, which only yields these thin, shallow layered type clouds. Pretty soon we'll start discussing these different types of clouds and how different lifting mechanisms and degrees of instability can form them. But for now, you know the drill.